So hello everyone. Today I'd like to talk about perceivers, this kind of model, and I'd like to share what I've learned and why I feel this line of work is quite interesting and also relevant to what we are doing at Apple. So as the title implies, perceivers are a family of modality-agnostic architectures. And so I will first talk about the motivation and the challenges we are facing. And then I will introduce Perceiver and its subsequent works, Perceiver IO, Perceiver AR, and I will summarize with some takeaways. So yeah, how I got to know Perceiver in the first place. I think Flamingo we've discussed in our study group a million times. So you can see that, so yeah, what really caught my eye was really the perceiver resampler in the middle here. And it really sits between the visual component and the language model. So it's serving as a bridge between the two modalities. So it turns out that perceiver architecture has been an integral component of multiple other works. For example, this is the recent work also from DeepMind, like 3D reconstruction. They are using perceiver as a general perception model to provide bounding boxes. So yeah, that's why I feel it's quite interesting, and also it really rang a bell when I saw the name, because I think it was also quite famous in the long sequence community, and I will talk about long sequence problems later. Yeah, and also please feel free to interrupt me if you have any questions. So first, let's motivate why we need general architectures. So as we know, like humans interact with the world with multiple senses. We see, we talk, and there are also different modalities with different data shapes and structure. The common approach to cope with different modalities to impose human knowledge, right? For example, for images, we know like if we have a pixel, then the surrounding pixel could express the same feature, right? It could be my hair or my body, and so we use convolution to upsample those features. But why don't we want these kind of strong architectural priors? This is because if we were to use this kind of architecture, we need to design fine-tune even a specific architecture for each modality, which is not sustainable, and also it doesn't take advantage of the increase in compute we are having. And yeah, and I highly recommend reading the beta lesson from Rich Sutton, who is the godfather of deep learning. And another thing I'd like to get straight is long context, right? Why do we need million scale or thousands of tokens to fit into our context? And I always like to pull up this example. So for example, in this image, I would like to predict the token at this position, this Pokemon hat. The simplest way we can do is to just copy pixel by pixel from the top to the bottom, right? But in that case, what we need is to really to fit all the pixels prior to the position we're predicting at into our context, so that the model can pick up the useful information and do the copying task. Actually, in the long sequence community, there's also a benchmark just for copying task. So in the ideal case, so in the real world data is sometimes our long sequences, for example, high resolution images, books, music generation. And in the ideal case, we would really cram all the tokens into our context so that the model can pick up whatever it wants to learn the useful information to make the prediction. But in practice, we need to really pick smartly the useful tokens and to fit into the context, the limited context. For example, birds, we only have 512 context length. Otherwise, the model has to make a hard inference without the useful information. And this actually is an old desire, like for example, long form from 2020, Combiner, Performer, Big Bird, etc. So it's quite saturated in literature. And what are the challenges? I think, so the challenges are the bottleneck of compute and memory of transformers. Transformers are very powerful and general architecture because it doesn't make assumption as to what specific relations there are within the context. It will compute the pair-to-pair relationship score or similarity scores between each pair of tokens. It doesn't make any assumptions, but this really induces the quadratic complexity, right? If we have M tokens and L layers of MLP, then we will have this kind of complexity. So this is the full attention. So in the literature, people will have this sliding window. We only compute, we only assume that nearby tokens are more important than far away ones. And we can do dilated ones or even the combination of both. So brick and brack, all kinds of techniques have been employed. And also, different modality data has different structures, I have said, and generating multimodal outputs is also quite challenging because currently transformers can only do text in and text out. So this is where I'd like to introduce the perceiver architecture. The key ideas are the following. So as we can see, we have key value and query as we had before, and we have the binary, which is the input. So the green ones are the input as usual. For example, this is serialized images. And what it does is that instead of forming all key value query pairs from the input, it constructs from directly construct the latent array. And so the latent array has dimension n, which is independent of the input size n. So in this case, it's so-called decoupled from the input size. And what it does is that it replaces the first layer of self-attention with a cross-attention, and the cross-attends allows the latent to cross-attend to the input. And then in the following operation, it's iteratively refine, if you like, the latent representation. And we can have whatever numbers of layers we want. And then what's interesting here is that you see there's another input. So the input doesn't only come at the beginning, but also in the middle of this resampling process. So I think the rationale behind this is that the authors want to really extract the useful information as much as possible in case you miss something with this small latent array. And typically, n is much smaller compared to m. Is smaller than 1K typically. And we replace the first layer of self-attention with the cross-attention. So that's the key idea. So the main contributions, therefore, is a general architecture where we have we impose few structural assumptions on the input, while we still enable very long sequences because we can just serialize all of them. And it's really meant to build an end-to-end model agnostic learning. And because we have the m latent array, latent m number of latents, this really decouples, n number of latents, this decouples from input m. So now we have the complexity m times n for the first layer of cross-attention and the subsequent L layers of self-attention. And another thing I'd like to mention is that because we don't impose any modality-specific information, the authors use Fourier features to add additional position information, spatial information to the model. And this is automatically sampled from the Fourier sequence. Another contribution is that they achieve comparable performance on multiple modalities with only one simple architecture that I just showed. So here's the evaluation. I will zoom in for the second table. Sorry about that. So first, on the images, they evaluate on ImageNet, and the shown here is our positions. The higher the better. And we can see the red, so the models in red are like very modality specific, and you can see when they operate on the raw inputs, the accuracy was fine. But if we input the image in a permuted way, meaning that we reorganize the pixels within an image. So basically, if you see the dataset permuted ImageNet, you will see gibberish. You don't see a cat or dog because all the pixels have been rearranged. But if you see the perceiver, because we don't impose any structure assumptions, we don't use convolution to sample the image, we only use the Fourier features as position encoding. If we switch to the permuted ImageNet, the performance doesn't drop in this case. What I'd like to highlight is that the performance here is not the state of the art. I think what they want to show is that the performance are comparable, but it's not it's not comparable to the state of the art. Sorry, Peter.
Thanks. Wait, the permuted one, I didn't get this. You mean they literally randomized the order of pixels, or like what does permuted mean?
Yeah, that's true. So they permuted the pixels of an image. So the image, for example, from a dog to a gibberish image. So you can't see anything.
But is this?
But I think it would be reasonable to use different hashing functions for different images. I think the dataset is randomized So the location is not deterministic. I think that's what I want to say.
I'm actually surprised that it can be that good then. Like what positioning, like, I mean, aren't we back to histograms of colors basically, right? If you do randomize under pixel,
yeah,
like one of the random permutations just sorting by RBG value, right? And then, I mean, a human would not be able to interpret this, but I guess if you train a model, it would pick up, okay, there's more black in like nighttime pictures, that kind of stuff. But what else is there to go by then?
Yeah, I think that's a good analogy to make for the red models, because they really lose sight when you randomize the order of the pixels, because you can't convolute the patch by patch. One thing I forgot to mention is that the reason why perceiver can still do great is because the Fourier features are were added before permuting the pixels. So the location information is still there. Sorry, yeah. But
okay,
yeah.
so isn't it there's no way to pass this, but for the VIT, okay, but this is a patch encode. Okay, I mean that's a fake eval, right? Like because VIT cannot. I mean, right?
No.
Like VIT obviously couldn't provide the position because it's about a patch, and the patch would also be randomized, so you can't provide that information. Like,
Exactly.
This is heavily
yeah.
favoring the right?
Yes, but I think that's what they call the featurized position encoding, because as you can see, they all have been added the Fourier features, which indicates the location of the original location of the pixels. But and only a perceiver can pick up this information, and VIT and ResNet can't, because they have very specific assumptions on the structure of the image, original image. Yeah.
I see. They all have the. Okay, yeah, that makes sense. Okay, I get it now. Thank you.
Thanks.
I wanted to ask a question about there was a paper, I don't remember the title, I would first need to look it up, about actually showing that the capacity in neural networks, even like before VIT and transformers, was already so big that actually you could, I think, randomly permute ImageNet.
Yeah.
Like, and then you still would have such a memoization capacity in the network that you could still kind of retrieve the right classes with, which, I mean, yeah, it would be kind of interesting to review this in the context of these perceivers. I'll try to find it, and maybe again it would be okay.
Nice. Yeah, that would be great. Thanks, Marcin. Yes, and for audio videos, by the way, they're also still using the same architecture. For audio video, I think I will just zoom in here. If you can see. So for audio video, here they are comparing with other models. So first they input, so I think the benchmark were conducted on audio set. and the scores are higher. The higher is better, and here you can see when we only feed the audio inputs to the model, the performance is comparable with the baselines. And when you only feed the video to the model, it's much worse than the performance with only the audio. But when you add them together, it seems that the model can pick up more information utilizing more data to achieve a higher score. What's surprising to me is that, say, if we look at the second line, when you add the Mel spectrogram, the performance is actually not going up that much, because I think from literature, when you have transformed the raw audio to a spectrogram, raw Mel spectrogram, the performance typically goes up by quite a bit. Maybe there's a bug or something, but yeah, that was interesting to me. And another benchmark they've done is the point clouds. Basically, the point cloud data sets, for example, ModelNet 40 is where you have a bunch of points in a 3D space, and you want to predict what those points represent. For example, it's a sofa or cat or dog. And they also still achieved comparable results. It's not SOT, not state of the art, but still it's comparable. So I think what they're trying to show, in the paper is that this architecture is quite general and can achieve comparable results on multiple modalities. Some criticism here. I think the first one is it's obvious, right? Why the model can only output one single modality. In fact, all the benchmarks they have done are classification tasks. And the second is that the attention layers are, none of the attention layers is causal. So this really restricts the capability of generative tasks. And also, what's interesting is that if you go back to this slides, you will see for the learned position encoding, which in my opinion is the most general case, it is not performing as well as the simple Fourier features. So it's not strictly that general, because the most general case would be everything learnable. So that brings us to the Perceiver I/O, which really adds the multimodality outputs to the Perceiver architecture. So what it does is that, so if you mask out the bottom part, so the output query part, the up part is basically the Perceiver architecture, right? We have the input array here with the dimension of m and the channel C, and the latent array of dimension n. And typically this array is randomly initialized like Rn. And then you pass it to the encoding. So in the paper they call this input. And then you do a bunch of L layers of recurrent process to refine the latent representation. And then you pass it on to the output. And this, so the orange boxes are really the contribution of Perceiver I/O. So what it does is that it really adds back the modality-specific information via a set of queries to do a cross-attention with the latent array. Say we want to generate an image, reconstruct an image, then this would be the positions of each pixel. I will show an example on the next slide. And then we'll produce also multimodality output. So this is an example. For example, so this is an input image. The goal is to reconstruct the image. What it does is that the model puts the image through the encoder, construct the latents, and put to the decoder. And in the decoder, what we do is that we put the locations x and y as queries, and we query each and every single point in this image. So if we have 100 by 100 pixels, then this would be 10,000 queries. And this is, the bottom part shows how we can query different modalities. For example, we can for the simplest one would be classification, because we just have a task ID. For multiple task classification, we have multiple task ID to query the classification output. And for mask language modeling, we would have a bunch of positions. They also test on StarCraft, which is multitask training. And the multimodal autoencoding, they introduce so-called modality-specific tokens, like is this video, is this audio, and stuff. For audio, we have the time span. For video, we have both time and location, and so on. So the main contribution is that, yeah, it really enables multimodal outputs, and it's really at the same level as the inputs. It's quite general. And also it's quite efficient. I think they also improved the efficiency of their implementation. And I will show results where they removed the need for tokenization when processing text. So this is the results on language understanding. So what they did is to evaluate the model on GLOW tasks, general language understanding evaluation. SPS is the training step per second. So what I want to highlight here is the bottom part. So they compare with BERT with and without tokenization. So because the transformers generally can't cope with long sequences, that's why we have tokenization. We group tokens together, and typically, if without tokenization, we will have 4 times longer sequences. So in this case, say if when we remove the tokenization, the model will operate purely on bytes. So in this case, it's UTF-8. And what I wanted to highlight here is so because we removed the tokenization, the sequence becomes longer. So M is the number of input tokens. And for BERT, it really had to reduce the depth, because the model, otherwise you got I'm killed, has to fit into the memory. But for Perceiver, because it's a general architecture and it can efficiently process those long sequences, it keeps the same. The latent value keeps the same, and it also achieves comparable results. And I find it's very interesting. Another thing I'd like to mention is that it's really matching the flops. So you can see Perceiver is much larger in this case, right? But what they argue in the paper is that the reason why we can have much larger models but still matching the flops is because Perceivers are more efficient in terms of computation.
Because of that trick?
Yes, because of the latent refinement.
It's funny that they had to make a UTF-8 to make the task more complex.
Yeah.
It's basically just to show, hey, look at us, basically. But like you could have like you have like if you have like a classic sentence piece, they.
Yeah, I agree. I think they are really showing off by increasing the difficulty of tasks, because tokenization has different purposes. One is to reduce the length, and also another, I think, is reduce other implications in like processing text. I think prior work has shown that without tokenization, you have all kinds of complexity in terms of processing those tokens.
So you mentioned it went out of frame rate because the intermediate representation activation was too big.
Exactly, yes. So, for example, for BERT, when we increase the input length becomes larger, then the attention matrix becomes bigger. And then you need to reduce the number of layers in order for the model to work with the limited hardware. And also, as JP has said, actually those benchmarks are synthetically constructed for the purpose of testing out the model. But if you have knowledge about the data, for example, for images and the locality, then using them is definitely better. And another interesting task they've done is optical flow. So they evaluated this task on the Sintel data set. So basically, this task is to predict. So for this task, what we want to do is that given 2 consecutive frames from a video, you want to predict the location differences between 2 frames. And so, for example, I think the red is moving to a specific direction, and you want to predict where the character is moving. And they are comparing with, in this case, the state-of-the-art model, which has won the best paper award in ACCV. So this I checked it out. This paper is this architecture is really complex. It has like some 40 correlation volumes in space and time, and very specialized upsampling operations, and it's super complex. And it's interesting that we can achieve comparable results with a much simpler architecture of perceiver.
Then actually on the real data, because Sintel is a synthetic dataset, right? And then the KITTI is a real dataset. And then the error actually is still on the raft. This very specialized architecture is lower, right?
Yeah.
Absolute values are much higher.
Yeah. Yeah, that's a good point.
But I mean, still, it's very impressive.
It's still, yeah. But I think, yeah, you're right. I think on the real data set, the gap is still there. Some disadvantages is that I think it still has a very restrictive assumption as to how the outputs are decoded, right? So in this case, we are shooting those queries to the cross-attention one after another. So we are not making any assumption about how the output is organized or whether there is any locality in the output. And also, it still doesn't provide the autoregressive capability. So I'll quickly wrap up with Perceiver AR. So Perceiver AR is really, AR stands for autoregressive. So it enables this perceiver architecture to do autoregressive generative tasks. So for example, in this case, we have the original input. What we do is that we given the context. So the context would be the orange tokens, and we are targeting the red tokens. So in this case, we're predicting small r, a, and capital R. And what they do is that they're treating the targets as latent. So in this case, the latent would be the last 3 tokens, and we are basically shifting the causal masks from the cross-attention all the way to the self-attention layers. And so they call this end-to-end causal masking to enable the generative tasks. And they correspond each target with a latent array. So for predicting A, we construct a latent array of latents A, and for predicting R, we also construct a set of latents. And it's quite efficient. And also, I saw their demo on reconstructing videos, and I can really see the droplets in those videos. And it's quite impressive because they are operating on the raw tokens, in this case, raw pixels, instead of doing convolution or upsampling. And yeah, this is the case where I think it will be very interesting also for the on-device case, because what they also test out is to scale the resource usage at test time. So how they did this is that, so they really draw a parallel with the transformer XL work. So on the top is the transformer, vanilla transformer. What we do with transformer is that we given a long sequence, we can't process all of them, we do chunk by chunk, right? We process this, we predict token by token, then we move on to another one. And there's no information flowing between different chunks. And with Transformer XL, maybe it's the most popular one out there for processing long tokens, long sequences, is that they have this memory tokens. So they pass some memory tokens to the next chunk. And also they stop using stop gradients to prevent the model from back propagating to all the way to the start. And for Perceiver AR, what we have is that we have a first layer of cross attention where we allow the latents to attend to all the locations in the sequence, and then we do iterative refinement. And why they are saying that we can do test time scaling is that when we're training, we don't care, well, maybe we have a bunch of compute and memory resources, then we don't need to worry about the size of the latent. but maybe at test time we want to do something on device, then we can shrink the number of latents here to reduce the computation cost. So basically, we don't change the training process, but we change the number of latents during test time, which is different, could be different from the training procedure. And here is the result on ImageNet generation. So here you can see when you increase the number of latents, you get much longer generation time. And this is the bits per dimension error. Yeah, and the lower is better. I'm not seeing a very different performance drop. Another playful benchmark what they did was, so typically we have RGB 3 channels, and the way we process them is to really doing RGB in order, right? What they do is that in this case they do this sequentially. We process red pixels, then green pixel, then blue pixels. And what they are trying to show is that when we have very long context, the ordering doesn't even matter anymore. So we can put whatever order we want and still achieve similar results. In this case, it's bits per dimension, and the lower is better. And for language modeling, they also, what's very interesting to me is that they evaluate on this PG19 book datasets, and they really achieved state-of-the-art results. And they were very honest. They said that they are they overfit on this dataset by quite a lot because they can spill out the entire book if asked. So because you have the context to feed the whole dataset and the whole book in, and you memorize all of them. And for music generation, I will not play the demo here, but it's very impressive. They can generate music for minutes long, and it's you can hear the coherence there, and also the melody is changing, is repeating but gradually changing. And you really need very long context to capture this gradual change. And also they achieved good results on this dataset. This is a piano context dataset, and lower is better. So a quick summary. So Perceiver is a family of modality-agnostic architecture, and its subsequent work enables multimodality outputs, autoregressive generation, and also there's another work, Hierarchical Perceiver. If you are interested, you can check it out. And it really increased the receptive fields by even further by stacking on top of them, which is is not a new technique either. So that's it. Thanks a lot for your attention.
Cool presentation.
Thanks.
Awesome. I know we're already over time, but I think, should we take 1 or 2 minutes for questions? Of course, everyone that has to leave, you feel free to leave. We strategically have the team meeting that is in the same room. So actually we have time. It makes sense to just spend a minute or two on questions. Are there any?
Why is ChatGPT not using the Perceiver? We don't know for sure, of course, but presumably it's not using.
Yeah, that's a good question. Yeah, I think I read some of the discussions on Open Review. I think actually it's not as efficient as the